Hi everyone, my name is Noor-e and this is my lab 5 on collisions. So in this lab we will investigate one-dimensional collisions using both experimental observations and computational models. So our purpose is that we will first observe real-world collisions between two balls, we will analyze that motion using tracker, and then we will build a computational model based on the energy principle and the momentum principle. And then we will compare our predictions with our experimental data. To understand collisions, we need two fundamental concepts. The first is the conservation of momentum. This principle states that in an isolated system with no external forces, the total momentum must remain constant before and after a collision. This is incredibly powerful because it means we can predict what will happen after a collision just by knowing what comes before it. The second concept that we need is the energy principle, which involves kinetic energy. In a perfectly elastic collision like billiard balls colliding, energy is conserved, but in inelastic collisions, some of the energy transforms into sound, heat and sound or deformation. Understanding which type of collisions we are observing tells us a lot about what is happening. These are the assumptions that we need to make. First of all, our system is isolated. Second of all, our balls are rigid. We're assuming that our balls are rigid so no deformation occurs. Our motion is wide-dimensional, and we are ignoring friction and air resistance in our system. Here is a procedure that I use to conduct my experiment. First, I recorded the video of one ball hitting another, and then I analyzed the collision of the two balls using tracker. And then I constructed two GoScript models to model their collision. And then I compared and analyzed the differences between the experimental results and the model predictions to determine the collision type. So here is a tracker video that I analyzed. So to calculate our initial conditions, we took 2 points from our tracker analysis and we used that to calculate the initial velocity needed for our computational model. To predict collision behavior, we built a computational model in GoScript. On the left, you can see that our setup code during the initial conditions, we created two balls as blue and red spheres, each with 0.5 kg mass, and ball 1 starts at 0.13 meters with our measured velocity, while car 2 stays stationary at 0.525 meters. On the right is our calculation loop with a 0.002 second time step that simulates the collision and updates our graphs. So these are the two sets of data that we inputted into our computational model. Each contains time and velocity measurements from our tracker analysis. This while loop is where we actually simulate the collision. On the left, we calculate forces between the carts, update their velocities and positions, and read in our experimental tracker data to validate against the predictions. On the right, we smooth the velocity data and calculate the kinetic energy for both of our carts, then plot predicted momentum versus the experimental momentum. So here is our model, computational model simulation. These four graphs show the key comparison between our computational models and real experiment data. The top left shows the ideal elastic model's momentum prediction. It's perfectly smooth and clean. The top right shows the ideal elastic model's kinetic energy. It stays constant, exactly what we expected from an elastic collision. But look at the bottom row. This is our actual experimental data from Tracker. The momentum is noisy and fluctuates around the predicted value. The kinetic energy starts high but drops significantly after collision, showing clear energy loss. Comparing them, you can see that the experimental kinetic energy doesn't match the model's prediction at all. The energy decreases instead of staying constant. This mismatch tells us our collision is definitely not elastic. It's inelastic. So some of the possible errors that may have affected our results include tracker measurement inaccuracies, where small position errors get magnified in velocity calculations. Our collisions might not have been perfectly head-on, introducing unaccounted angles. Mass measurements may also have been slightly off, and real materials may deform during impact, affecting the energy loss. These are just some of the potential errors that may have affected our final results. So what if the balls stuck together after the crash? In a perfectly inelastic collision, the two objects stick together after impact and move as one. Momentum is still conserved, but the kinetic energy decreases because energy is lost to heat, sound, and deformation. What's interesting is that momentum doesn't change. The total motion stayed the same. In our experiment, our collision behavior came close to this perfectly inelastic scenario, showing significant kinetic energy decrease similar to objects sticking together. But what does my experiment imply regarding energy? Our experimental results prove something fundamental about the real world. The kinetic energy decreased after collision, so it cannot be perfectly elastic. Energy transforms. Some becomes heat and sound. Some goes into deforming the cart materials. The ball materials. This shows momentum is always conserved, but kinetic energy is much trickier in a real collision. Real world collisions are usually partially inelastic, not the ideal elastic models we study in theory. Thank you.